Welcome to these first office hours for the class on functional analysis. I am in my office here at École Centrale Paris, and I would like to thank all of you for joining this class. You are coming from 149 different countries. I hope you enjoyed this first week, which was about topology. You saw that if you changed topology, then you changed convergence. So different topologies will lead to different types of convergence. And soon enough, we will have different types of convergence. We'll have the weak convergence, the strong convergence, the weak star convergence, all of this. So this will be in a few weeks. For now, it is important that you understand what is a topology. It's important that you know how to work with them, and that you can actually understand how convergence works, and also how continuity works. I have a team with me. There is Anna, of course, who is doing this MOOC with me and who is writing the PDFs and also who is very active on the forum. There is Caroline, who is doing an outstanding job as a pedagogical engineer at Centrale Paris, and she is working on all technical aspects on this MOOC in connection with the team of Coursera. We also have two final year students at Centrale Paris, Kayum and Pauline, and I would like to thank them very much for helping us with this MOOC. And Kayum is also the class president, so on top of all of his responsibilities, he took on the fact that he will be helping us with the MOOC. Thank you very much to both of you. We also have Leonard, who was a student during the last session of the MOOC. He did a wonderful job last time. He had wonderful, outstanding results, and we invited him to help us with the forum. So some of the responses might be from Leonard, and we'd like to thank him very much for joining us for this MOOC. The team told me that I should answer two questions during these office hours that were asked quite a few times on the forum, so I will do just this. I will answer these two questions. The first question is about contact points versus limit points, and understanding what is the difference between the two. The second question regards what is compactness, or more specifically, the proof of 0, 1 being a compact set. So I will answer that second question as well. So let's start with the first question. What is the difference between a contact point and a limit point? The definitions were given in the PDF document. It's actually definition number 6. So if you haven't read the PDF document, you probably don't know what is a contact point and the limit point, let alone what is the difference between both of them. It's okay. You're going to learn about this during these office hours. So let me first recall the definitions. We start with the topological space, capital X. Small x, being an element of capital X, is called a contact point of a set A, which is a subset of X, if every neighborhood of X contains at least one point of A. This is the definition of a contact point. Now, a limit point, this point X, small x, which is an element of a topological space, capital X, is called a limit point of a set A, included in X, if every neighborhood of X contains at least one point of A different of X. So from these definitions, it seems that limit point is more demanding than contact point. And indeed it is. I mean, if you are a limit point, then you will be a contact point, but you could be a contact point without being a limit point. The best way to show you the difference is just giving you an example. Let's take X, the topological space, to be R, the set of all real numbers, and let's just choose the usual topology. Now, we're going to choose a set, capital A, which will be 0, 1, opening 0 and 1, union with 3. So you see it's all real numbers between 0 and 1 strictly, and the real number 3. Now 3 will be a contact point, because indeed every neighborhood of 3 contains at least one point of A. Well, that's going to be 3, by the way. So it's a contact point. It meets the requirement, meets the definition of a contact point. But it does not meet the definition for a limit point, because every neighborhood of x will not necessarily contain at least one point of a difference from x if x is equal to 3. The example is the set 2, 4. 2, 4 is a neighborhood of 3. But if you look at the intersection between 2, 4 and A, you will only have 0.3. So what I'm saying is that it will not meet the definition of a limit point. Now, if you look at 1, 1 will be a limit point, but it will not be an element of the set. So you see, you can be a limit point or a contact point without being an element of the set. Alright, so I hope that this clarifies the difference between contact points and limit points, and that it answers the questions that were asked in the forum. The second question was in connection with the proof that 0, 1 is a compact set. And that is in video 1.4, around minute 7. I proved that 0, 1 is a compact set by building a set A, which is the set of all real numbers x in 0, 1, such that we can extract a finite subcover of the initial cover for 0x. And what I prove is that A has a supremum, which is M, and then I worked with the 0m, saying that M is in A. And a lot of people ask, why is M in A? And they're saying that I'm going a little fast here, and I guess I am, so I'm going to explain to you why indeed it's true that M is an element of A. M is covered by an open set of S. Based on the definition of open sets for the usual topology of R, it means that there exists an epsilon positive, strictly positive, such that M minus epsilon, M plus epsilon is included in this open set. And we will denote by V this open set. Now, if it works for this epsilon, it will work for an even smaller epsilon, provided, of course, it is strictly positive. What I'm saying is that I can choose an epsilon small enough so M minus epsilon over 2 is not negative, and what we will have is that M minus epsilon over 2 belongs to A. Remember that M is the supremum of A, so M minus epsilon over 2 will belong to A, provided again that epsilon is small enough. This means that there exists a finite subcover of S for the interval 0 M minus epsilon over 2 by definition of the set A. Now we'll call S index epsilon over 2 this finite subcover of S for the interval 0 M minus epsilon over 2. So what we have is a finite subcover that covers the points between 0 and M minus epsilon over 2, but we also have this open set V that will cover the points between M minus epsilon and M plus epsilon. So in the end, what we have is that S epsilon over 2 union with V will cover 0M, and it will also be a subcover of S, and even a finite subcover of S, because I am doing the union of a finite number of open sets and one open set. So if it's a finite union 1, then it will remain finite. So what I have here is that I can build a finite subcover of S for 0M. And this exactly means that M belongs to A. So I hope this clarifies the proof for the compactness of 0, 1. So this is the end of these office hours. I suggest you keep posting questions and answering questions on the forum. It's a wonderful way to learn. Also, you may want to follow me on Twitter. The call sign is @Kenyol. And don't forget to submit your quiz and your write-in question by Sunday, 11:59 p.m. Paris time. Be careful, it might be earlier in your time zone, and you may not want to wait until the last minute to submit your work. I, of course, encourage you to do this. It's really important that you take the quizzes and do the peer grading. I will see you next week. Between now and then, have a great week.